Okay, um, welcome back to another video. Today I'm going to be doing problem 5 from the discussion worksheet. You can find this problem under, I believe, week 2 kinematics in the B courses, section 106 and 112. And this was I think like the challenge problem, or at least the most challenging problem. And I'm gonna just walk through it. So we can read this together. Basically, the gist is there's an airplane, draw airplane here. Okay, and it's on a runway. And it must reach a takeoff speed by the end of the length of the runway. It must have a final speed of at least VTO in order to fly. And they're saying it can be increased by unloading some of the luggage, which is kind of unimportant. So like when you're reading a question like this, you probably want to only focus really on the important things that it's giving you and then trying to answer the question. So let's start with this. What is the minimum acceleration A needed to achieve takeoff speed and length L in terms of known variables? So known variables are basically going to be VTO and L. So if the plane starts at rest, let's say over here at 0, let's define this as the positive direction, positive x direction. If it starts at rest, that means the initial velocity is equal to 0. And so if we then think about what variables we have initial velocity, we have a final velocity, which we're solving for, or we're not solving for, but going to be solving for, sorry, and we have a length of runway. So if we think about this and we're looking for acceleration, the only equation that really matches up with this is the equation that combines the first and second integral of acceleration. So this is that set equation. So I'm going to go through, and also just to be clear, we're doing part A of this. What is acceleration? So I will go through and do each of these. So V final squared is going to be equivalent to the VTO. So VTO squared. And the initial velocity is going to be 0 because it starts from rest. And then acceleration is what we're solving for, and the change in x is going to be L because we're asking for the minimum acceleration to basically just start flying when we get to the end of the runway. So now all we have to do is a little bit of algebra, and what we can do is we can divide by 2L, and then we get A equals VTO squared over 2L. So that hopefully was simple enough. If it's not, maybe have a little more practice with the level 1 problems, because I believe this is what the professor would consider a level 1 problem. Anyways, so problem B says after unloading some of the bags, so your acceleration will be the one you calculated in A, you must compute VD, which is known as the decision speed. So VD occurs before VTO, which is this, and has the following property. As you accelerate on the runway, should an emergency arise before reaching and up to velocity Vt, you can stop the airplane within the runway length by applying maximum braking. Maximum braking for your airplane results in an acceleration of minus b. And it's asking us to calculate Vd. So this was a lot. Basically, the important stuff is we're having a new variable included and another new variable, and we're solving for Vd. So the best way I can try to explain this is with a position. I think position versus time would be, actually no. Let's do velocity versus time graph. So, if this is velocity and this is time, so we start off and we're going, whatever, accelerating, and we're going up into a point which is going to be VB, right? And some random time, right? And then after that, we have to be able to decelerate back down, maybe not all the way back down, but decelerate, I guess, yeah, you have to come to a stop all the way back down, and this will have a slope of negative b, this will have a slope of a, and the area under here should be L. So, seems pretty simple, but we're going to find out that it's a little bit more complicated than that. So what I noticed directly from this problem is that they're not giving us a time variable, right? And having a time variable would mean we'd have to add extra unknown variables, which we can do if it gets to that. But usually you want to try and not do that, typically. So anyways, let's start off by making a equation that represents this whole section, and then an equation that represents this whole section. So we'll start with the blue. So this one is going to be kind of easy. So again, we're going to be using the same exact equation, v squared. This is probably like the most helpful equation for this class because it seems like most of the questions he asks don't really include time, which is kind of interesting. I think it's something you don't have to use like the quadratic formula that much. But yeah, interesting thing to note. So yeah, and I am also going to just define another variable just to make this problem a little bit simpler, which I will call x1, which we don't have to necessarily solve for, and x2, which again we don't really have to solve for, and the relationship I'm giving is the length equals x1, sorry, wrong color, x1 plus x2. And so by doing this, I'm able to split up the change in x into two pieces. I'll just put them back later, but this will let me have two clear equations for each part. So, starting with the first equation, which is a blue equation, we will go from this, v squared, our final velocity at this point should be vb. So we're given vb squared. Our initial velocity is going to be 0 because we're starting from rest down here. And our acceleration is going to be given by 2a, and then technically we already solved for what acceleration is up here in the first half, so we could plug that in if we want. I'll do that at the end just to keep things a little bit simpler. And so finally the change in x is going to be x1. So if it's a little confusing why I'm allowed to create new variables, I'm not really sure the best way to explain it, but sometimes it's easier when you create new variables that are just pieces of a different variable. So basically, yeah, so we're left with this equation for our blue, and for our red, x2, we are going to do the exact same thing. So the only difference is our final velocity this time is again going to be 0 because we're coming to a complete stop. Our initial velocity is actually going to be vb squared. Pretty interesting that those are the same. And then we are given a deceleration this time. So I'm going to write negative because we're going that way. And we're allowed to use the variable b in our answer. So it'll be 2b x2. So now we have two equations, and basically we just have to relate them in some way, which ends up being this. So now, if you notice, we have three unknowns and three variables. Three equations. So all we have to do is solve for one and the other, and then one and the other again, and then solve for our final VB, which is what we're trying to go after. So basically, I'm going to solve this equation for x2. So let's see. x2 equals L minus x1. Okay, so now what I can do with this is I can plug in this for x2, and then for my red equation, I get 0 equals VB squared minus 2B, and then it's L minus x1. Now, what I'm going to do is I'm going to take this equation, sorry if it's getting a little messy with all the stuff, I'll clear it up by bringing it all down. I'm going to solve this equation for x1 and plug that into here, and that should eliminate all of the unknown variables except for VB, which is what we were solving for. So if we take our blue equation, VB squared equals 2ax1, solving for x1 gives us x1 equals, not 2, VB squared over 2a. Okay, and now when we plug this into here, we get 0 equals VB squared minus 2b L minus, I'm going to make sure I draw the b a little bit smaller so I don't get it confused with this b, VB squared over 2a. And so now all we have to do is use the distributive property, distribute each of these out. We get 0 equals VB squared minus 2 big B L minus 2 big B V little b squared over 2a. So if we notice, this looks like a pretty easy equation because it's not going to be a quadratic as, well, technically it is a quadratic equation, but we're not going to have to use a quadratic formula because there's no single VB terms. So what I'm going to do is I'm going to put this 2BL on the other side by adding it. So we have positive 2BL equals V little b squared minus 2 big B VB squared over 2a. And now I'm going to factor out VB squared. 2BL equals V, I'm going to draw the b smaller just so we don't get confused, VB squared. Then we have 1 minus 2 big B over 2a. This cancels to be b over a. I'll just rewrite it as b over a. Now, solving for VB squared, we get VB alone equals the square root of 2 big BL over 1 minus b over a. And so, just to check, it was VD the entire time. Oopsie. It's a little awkward. How far up did I make that mistake? I guess I've always been making that mistake. Sorry about that. It's been VD the entire time. That's sad, but it's the same variable, so it doesn't really matter. So yeah, so our VD, I guess, would be this. And you can sub in what you solved for A if you want in the above equation, and that would give you even better, but again, they're allowing you to use the acceleration negative b. So yeah. Okay. Now for the bonus question C. Accelerate on the runway as planned. you decide to abort VD, and you apply maximum braking just as you reach VD. Unfortunately, one of your two brakes immediately fails. Okay, reducing your braking capacity to be B minus 2. Okay, what will be your velocity at the end of the runway? Okay, so basically I'm going to again draw a velocity versus time graph, just because I believe that will be helpful in aiding us in this problem. We have a velocity here, time here. So we're starting off our normal acceleration, slope equals A, right? And then we get to VB. At VB, we're like, uh-oh, we got to start slowing down, but whatever, something breaks. And so at some point, this is a slope of negative b over 2. At some point, this area under the curve is equal exactly to L, and that's where you want to calculate the velocity at. So, again, how do we do that? So, like the problem B, we are not given a time, so we have to use the best kinematic equation, which is v squared equals VO squared plus 2a delta x. And so I'm going to assume that we are allowed to use VB as a variable, because we've already solved for it in the other problem. So theoretically, we could plug in our value for B and for A into this equation. So it would be kind of redundant to resolve for those. So what we're going to do now is we're going to assign values. So let's pretend like we are right here. And so basically, let's actually see if this will work, because yeah, we might still have to make two equations. Okay. Let me think about this. Yeah, we might have to do two equations. Let's just see how this works out, though. So I'm going to start this time by making the second half equation, which I'll call red equation. So we know that our final velocity, oh, that's what we're solving for. I'll just call it VF. Our initial velocity will be VD. I'll write it correctly this time. And our acceleration on this half is 1/2 b times 2 is just b. And the delta x that we're going is going to be basically L minus some x1. And by some x1, I'll call the area under this part of the curve x1. Okay, did not mean to undo that, but whatever. So unfortunately, it looks like we're going to have to solve for x1, which is completely fine. But yeah, so again, since we're not given any times, we're going to be reusing this equation. So let me make a x1 equation, and I'm going to use blue. And so this equation is going to, again, represent, what is everything keep deleting, this part of the graph. So we have v squared. So our final velocity should be vd squared on this part. This is equal to initial velocity, which is given as 0 because we're starting from rest at this point, 0 velocity. And now our acceleration is just going to be a, the same a that we solved for in part A. Confusing, I know. And the change in position is going to be x1 minus 0, which is just x1. So now what we can do is we can resolve for x1 like we did in problem B. And we can plug this in. And then We're almost there. So I'm going to use black now to show the final equation. So VF squared equals VD squared minus B. I'll actually fully distribute it out. BL minus, oh, I guess it would be plus because it's a negative, BVD squared over 2A. And to get rid of the square root, I'm going to get rid of the square, I'm going to square root both sides. So that gives a final velocity of this value. And if you wanted to, you could plug in our answer from the other parts into VD and plug in our answer from part A into A. But I don't think that's necessary. So let's spend this problem. If you have any questions, feel free to comment them. I will also be probably only doing maybe past exam problems or difficult worksheet problems like this, or homework. Oh, not homework problems, because yeah, I don't think it's smart to do homework problems. So yeah. So let me know if you have any other questions, and if you have any problems you want me to try and solve. So thanks for watching, and bye.